Hey, Plumber Tom here. If you're studying from the Mathematics for Plumbers and Pipefitters book, you've come to the right place. I'm glad to help you with your understanding. Don't forget to check in the description below this video for access to books and resources that will help you with your understanding. There are online courses and other things that you can take that will help you prepare for a state test. When you purchase from those links, you're helping me to be able to create more great content. Thanks for watching. Hello, welcome to this presentation of Mathematics for Plumbers and Pipefitters, Unit 34. My name is Thomas, and in this presentation we are looking at elevation in a plan view pipe diagram. Let's have a look at what does that exactly mean. First of all, we need to take a minute to remember what's the difference between the different types of views on a plan. When we say elevation view, what does that mean? Elevation view is referring to a side cutaway type visual. Like you were to take the building and just cut it in half, move half of it, and look at what you're seeing from the side of the building. In elevation view, it can show you the different layers and levels and things that go into the vertical portions of the building. Sometimes pipe diagrams are shown in elevation view where we see the pipes coming up and it's helpful information. But more often, if we're trying to figure out where pipes are supposed to go within the building, we are going to look at a plan view. Now, the plan view is the bird's eye view looking down on the building. Say you take off the roof and you're just looking at walls. Where do they lay out and what do these rooms look like? That's the plan view. Most of our diagrams that we'll be using in Mathematics for Plumbers and Pipefitters are going to be plan view. But the problem with a plan view, when you're trying to illustrate the difference on elevation, is that you can't really show that the pipe is lower here than it is over there. You can just show where that pipe runs. Obviously, as plumbers, we know that a drain pipe's going to have a difference in elevation, a slope. But how do you indicate that on a plan view? Well, that's what we're going to get into in this section, is we're looking at a plan view, and we're going to add to that plan view pipe diagram the elevations, which are going to give us specific information about where the pipe needs to be, how deep it needs to be, or what slope it needs to have, based on that overhead view and specific measurements that we have, or elevations that we have at points along that plan diagram. Now, most measurements, as is pointed out in the text of a pipe, are measured along the center line or in the center line of the pipe. When we are dealing with a plan view and elevations, like we are in this unit, we're going to be measuring to what is called the invert. This is a new term here in this unit. The invert is referring to the inside bottom of the pipe. When we're measuring down to an elevation, that's where we're measuring to, bottom of pipe. I might even say, make it easier, just call it the trench line, right? Whatever layer we're laying the pipe down on. But the technical point would be inside bottom of pipe. This is sometimes referred to as invert elevation, abbreviated I.E. You will see this on plans occasionally. It'll point to a specific place along the pipe, maybe where it's passing out of the building, and it will say IE and then give an elevation number. So this is how we can really determine exactly how deep the pipe needs to go. Now let's talk about where invert elevation becomes really important and useful to us, applicable to our daily work. And that would be if we're going to start a building and we need to know if the depth of our drainage system is going to meet the sewer out at the street. If they give us an invert elevation, and we know our benchmark, we can actually check. We can go pop a manhole, see how deep it is, knowing that we have to be at a certain elevation below building, and then finding out how deep that is at the sewer, and we can find out if we're going to make it. There have been situations when I've done installations, and we put the pipe at the invert elevation without checking, and then it ended up lower than where the sewer is out at the street. And we had to make some modifications. So these measurements can help us ahead of time to make sure we've got enough slope, that we're going to hit the sewer, that we're going to be able to make it. And that's really important information. All right, at this point, it's going to be really important that you follow along with me in your book. We're going to the sample problems, and actually there's only one sample problem in this unit. But within this sample problem, there are going to be 8 different answers or calculations that we need to come up with. So this is going to bring us in, and we'll do a bit of math on this to figure everything out. Then I'll turn you loose, and you'll have 2 exercises that are doing the same thing. So if you follow me here and see how we do this, you just apply that to your exercises. You should be fine. You see here on sample problem 1 that we have a plan view. We're looking down from above. We don't even get the wall lines, but we see where the pipes go. This is a pipe diagram in plan view. We see what the fittings are. There's a couple of 90-degree elbows at the top. You see a 45 on the right side, a Y down on the lower left. And all this information is important and useful. What we are asked to do is, first of all, find out the center-to-center measurements between each of these pipes for J, K, L, M. Yeah, for those 4. Now, we did this before in previous years in our math, so this part of it is going to be somewhat of a review. But going forward, what we're going to do is find our elevations at certain points. If you look on the diagram, we have A. Point A is right there by the Y. Point B is at the top on the left side, 90, looking up. Point C is at the 45, and point D is at the right side, 90, as that's looking up. What we're going to do is find the elevation differences where those should be, and they give us right here on the diagram, 1/8 inch per foot is our slope, or pitch, as they have it there. So that'll be our process. First, we're going to find our measurements. That's going to give us a distance to which we can apply the 1/8 inch per foot, and then we'll use those differences, add them to our elevations, and we'll be able to tell at any one of those points where that pipe should be on an elevation. Now, our starting point elevation is going to be 92.0. You can see down at the bottom. That's where we'll start, and then we'll add to that as it slopes up. So let's get started. All right, we're going to find the center-to-center measurements for J, K, L, and M. Let's start off with J. If you look there on the diagram, J is actually given to us. It's the section from the 45 to the 90 on the right side, and it's given to us as 8 feet. Not too much involved there. Let's find K. K is going to be the measurement from the 45 down to the Y that's on the lower left side. You can see it's a diagonal, and we're going to need to figure out a little bit of triangle math here. We can see the distance or offset between these pipes up at the top. There's 15 feet between these pipes. That gives us a triangle that looks something like this, right? With 15 feet here. We know exactly what to do with that when we're dealing with 45s. We're going to take 15 multiplied by 1.414, which will give us 21.21 feet. Now we can convert that 21 feet and 0.21 feet. If we multiply those feet by 12, that's going to get us into decimal parts of an inch. So 0.21 times 12 is going to give us 2.52 inches, 21 feet, and 2 is pretty close to a half, right? 0.5. We'll just call it 2.5 inches. All right, that's K. 21 foot, 2.5 inches. What about L? L, if we look at it, let's move our calculator here. L is the section at the bottom from the Y to the outlet as it's going out of the building or away from this section. We have an overall of 28 feet. And up above here, we've got a couple measurements to play with. First of all, we know there's 8 feet from those upper 90s to that first 45. Then we also know there's 15 feet from that 45 down to the Y. So basically we're going to take 28 and subtract both of those measurements, 8 and 15. That's the same as 28 minus 8 plus 15 is 23. L is going to be 5 feet. Let's have a look at M. M is just going to be the combination. We already figured that out, right? Up above there, the distance from the Y all the way to the 90 at the top is going to be that 8 plus 15 feet. And that's going to give us 23 feet. All right. So we have figured out J is 8. K is 21 foot, 2.5 inches. But I'm going to point out it might be helpful for us to keep our measurement also in decimal because we're going to be dealing with some elevation. We'll see how we end up using that. L is 5 feet and M is 23 feet. We have solved half of this sample problem. Now we need to use this information, calculate for those elevation changes. We'll multiply each of these by our 1/8 inch per foot, and then we'll add that to our starting elevation and see what we end up with.
Hey now, just because I talk monotone when I'm teaching math doesn't mean that you have to fall asleep. It's time to stand up, shake your limbs, wake up your brain, cause we've got more to come.
All right, let's start with our calculation for the elevation. That's A. A is the point at the Y. It comes from our starting elevation, which was 92. That's going to be important information for us, 92.00. And it's going to come up from there a certain distance. Now we calculated that L is going to equal 5 feet. And we know that our grade is 1/8 inch per foot. So if we take 5 times 1/8, that's going to give us 5/8 of an inch. Now let's follow the book's method and just say that basically for every 1/8 of an inch, that's going to equal 0.01, but we have 5 of those. When we convert that into decimal feet, so we've got 5, basically 0.05 decimal parts of a foot that we're going to add to our elevation. So we start with our elevation, which is 92.00, and we add to that our 0.05. All of those are decimal feet. And that's going to give us 92.05 decimal feet. That's what we get for our elevation at point A. All right, let's solve for B. Our elevation at B. B is going to be all the way up at the top by the 90. So we're coming straight through. And our starting elevation again is 92 feet. What is the total distance it travels? Well, we calculated L was 5 and M was 23. Really, it's like all along the side there. If you look at that, it's the same, 28 feet, right? So we take our 28 feet, times that by our 1/8 inch per foot. That's going to give us 28 over 8, which is equal to 3.5 or 3.5 inches. Now, if I take that 3.5, and that's in inches, I want to get that into decimal feet. I'm going to divide by 12. And what that's going to give me is 0.29 decimal feet. Now I have something that I can add on my elevation to that 92. So I take my 92.00 feet, and that's our elevation. It's coming up from there. So we're going to add, and that's going to be 0.29 decimal feet. Our total then is going to be 92.29 decimal feet. And that's what they're giving us there for B. Next, let's calculate for C. C is the elevation that we find over at the 45. So we've come from our starting point at 92.00. It comes through the Y and over to the 45. Start with our 92. What is the distance that we've traveled? Well, in L, we traveled 5 feet. K, we traveled 21 foot, 2.5 inches. But when we're calculating at an 1/8 inch per foot, there is a little bit in that 2.5 inches. But for our calculating purposes here, the text is just bringing us to whole feet. Let's just say 21 feet. And we're going to calculate our slope 1/8 inch per foot for all of our whole feet. That would give us a total of 26 feet that it travels, and a little bit with inches. But let's go 26 times 1/8 inch per foot. That'll give us 26 over 8, which equals 3.25 or 3¼ inches. Following me so far? We just kind of sped through those conversions, but we have a difference of 3¼ inches. Now let's convert that over into decimal feet. We take 3.25, divide that by 12, and that is going to give us a 0.27 feet, which we can add to our 92. Our elevation was 92.00 feet plus 0.27 feet, and we're going to get a total of 92.27 is our elevation at point C. All right, let's go to our last elevation, which is D. And on this one, we're going to travel from the 92.00 starting point. We'll follow this through from L, going to the Y, then we'll come across to the 45, that's K, and then up to the top 90 through J, and we have that 90 at the top, that's our point D. Okay, basically 3 distances we have to calculate into here. J was 5, K was 21.21, and J is 8. Now, I'm going to point out here, the book is a little inconsistent between example elevation C and elevation D. They did not include the 0.21 on elevation C. I don't know if they just forgot it or they're rounding, but in D here, we're going to use it. To be accurate, C should have included that 0.21, really, right? Just kind of following through here. All right, so we add those all together, and we're going to get a 34.21 decimal feet. Multiply that by our 1/8 inch per foot, and it's going to give us, let's use our calculator on this one, 34.21, and I can divide that by 8. Same thing, right? That's going to give me 4.27, and they're going to round that. It's pretty close to 4¼ inches. So that's what we have to work with. Now, let's just convert that over into decimal feet. 4.27 inches. And we're going to divide that by 12 to get us into our decimal feet. So if I divide here by 12, that's going to give us 0.356. I think we ought to round that up to 3.6. The book leaves it at 3.5. But basically, there we are, 0.35. And that's what we can add to our 92. So 92.00 plus 0.35 feet. We're going to end up with 92.35 decimal feet at our elevation point D. All right, now it's your turn to do some exercises. Hopefully this explanation of the sample problem will help you. It's going to be step-by-step, same process. Exercise 1 actually has less calculations. You're just doing J, K, and L for the distances, and points A, B, and C as you're figuring for elevations. On the next exercise, this is on the next page, we're talking page 132, there's a little bit more detail and a little bit more that you'll need to think through. So if you look at your book together with me, open that up. Notice there's an elevation, it's 95 feet, and that's at the foundation where the pipe passes from the building. But there's an additional 5 feet past that, so when we're figuring for J, we're going to include a little bit of extra. You'll also notice that the foundation wall itself is 1 foot. You're going to have to add that distance in. So pay really close attention on number 2 here. You're going to need to use what you know about triangles. Really rely on that 45-degree triangle to figure out distances. You're going to need that for N. You're going to need that for L. Pay close attention to all of the measurements on the diagram. See what you can do. Good luck with your exercises, and I will see you in the next unit.